students, welcome back to my channel, and today we will continuing with theory of computations. Now today we will see at a very simple computational model called the finite state machines or finite automata. In simple language, what is the intuition behind them, and why do we even need to study it? Okay, intuition for finite automata. Okay, so first I will give you an in simple language, what does a computational model means. Okay, so a computer. If I ask you what is a computer, what will you tell someone if somebody asks you what is a computer? So but computers are something which takes an input, it does some processing to that input and give you an output. But if you want to represent a computer, how does it taking an input and then computing and finally converting it into an output? It's in mathematical representation, it will be really, really complicated to represent it. Now, to make things easier, to make the study of how a computer is reading input, how it is finally coming to the output, the study of it, to make it simple, what do we convert a computer is converted to a computational model. Computational model means this is a simple version of a computer. Simple version of a computer. Version of a computer. And we represent only the parts of the computer which are necessary to study. Okay. For a particular problem, only the parts which are necessary to study, we will keep those parts in the computational model and we will ignore the other complicated stuff. Okay. So keep only the necessary parts of computer. Okay, so this is just a simple version of the exact computer. All right, in easy language. Now we will come to finite automata. Now finite automata, it has finite memory or extremely limited memory. Extremely limited memory. Okay, very less memory. Now you will be thinking, with such a less amount of memory, it cannot remember many things like a computer, original computer can do. So you will be thinking now, what are the examples how having such a limited memory can be useful in the practical world? Well, I can give you examples of computational models with limited memory. Okay, example can be your microwave oven. Microwave oven, the automatic doors that you see when you enter or leave a shop, automatic door controllers, your washing machines, washing machine, vending machines, vending machines, and etc. These are examples of uh, computational models, or they are computing something, right? Something is happening. Digital rich wrist watches, when you press a button, something is happening, right? And your elevators are also examples of machines which are doing some computation on an input and producing output, but they have very limited amount of memory in them. Okay, so we will see the example of automatic door controller. Let us see the top view of automatic door controller. Okay, the top view of an automatic door controller. So suppose this is the door. Okay, this is the door of a shop, and this is the front pad. Okay, this is the front pad, front pad of the door, and this is the rear pad of a door, rear pad. Now what do we want, how do we want this door to work? Okay, now it will be in two states. This door can be in two possible states. First is open state, second is closed state, right? We need to keep track only of the state the door is currently in, and if whether somebody is standing on the front pad or rear pad or both or neither. So these can be the possible inputs to the automatic door, right? Open, closed. These are the states of the door, and these can receive inputs. First input, suppose the door is currently in the closed state. Initially it will be in closed state, right? And then what happens? Somebody stands on the front pad, right? So what will happen from closed? It will go to open state, right? Now it's in open state. If the door is open currently, now what will happen when, yes, in open state, it is currently open. Again, somebody, one more person stands on the front pad. What will happen? It will stay in the open state, right? Again, if we reach a front input, currently the door was open, another person stands in the front pad, then the door will stay in the open state, right? Now suppose nobody is standing on any of the pads. Okay, nobody is standing on the front or the rear. So what will happen? Nobody is standing, that means input is neither, and the door was open. Nobody, neither. So the door goes to closed state, right? Again, in closed states, we have already seen what happens when in closed state somebody stands on the front pad. What more input can be there on the closed state? That somebody is standing on the rear pad and nobody is standing on the front pad. So what will happen? It will remain closed, right? If somebody is standing on the rear and the door opens, he might get hit with the door, right? So rear pad, the door remains closed. Okay, now in closed state, suppose on both the pads people are standing, then also door will not open, otherwise the person on the rear might get hit. Okay, so both also the uh, the door remains closed, and if it is closed, nobody is standing on any of the pads, then again also it will be uh, staying closed. Okay, yes. Now in open state, what other inputs can be there? We have seen front, we have seen neither, right? Now if the door is open and on both the pads people are standing, then what will happen? It will stay open, right? It will stay open. And if somebody is standing on the rear pad and the door is already open, so it will be open in the open state only, right? So this is the state machine, or how computation would happen. This is the start state. Okay, how computation would happen, um, how a automatic door controller would compute when some it is sensing some input on the pads, right? What, which state it will go depends on currently which state it was. If the door state Based on door's state and the input got from the sensors, it goes decides to go on which next state the door will be in, right? So this can be represented using a state transition table. State transition table means there are two possible states for the door to be in. First is closed. These are the states: closed and open. These are the two possible states. And what input can the automatic door controller get? It can get either neither. These are the inputs: NEITHER, right? Front, uh, rear, and both. This diagram, this graph only, I am converting it into a matrix, okay? And based on this, if your current state was closed and you got from the sensors input neither, okay, closed neither, then you stay in the closed state, right? You will stay in the closed state. And this element entry is representing the next state or next action the door would take, the door controller would take. Similarly, closed, I am writing it fast because I explained it in the graph over here. So we will fill it in fast. Closed and front input. Closed and front, it will go to open. Closed and rear. Closed and rear, it will stay in closed. Closed and both, it will stay in closed. Right? Then we see the open one. Open in front would be open. Oh, in neither would be closed. Closed. Then on front, open on front would be open. Rear, rear. Okay, we have written open over here. It should be rear. On rear, it goes to open. And in both, it will stay in open state. So this is the state transition diagram, or based on the what the current state the door is in and what input it receives, what to do next or which state go to next is being represented by the programmer to the controller machine using this matrix. Okay, so or this is called the state transition table, okay, for automatic door controller. So now for programming this, okay, to in some programming language, we know that two unique states can be represented if you want to represent two unique values using some bits. So how many bits do you require? You require only by one bit, right? A 0 might represent the open state and a 1 might represent the closed state. So only one bit memory is required by the automatic door controller to keep a track with what is the state that the door is in, right? So it requires very less memory, right? Only one bit memory. And another example of a finite state automata would be an elevator controller. In an elevator controller, the states might be the floors. The floor it is in are the states, and the input would be the signal sent by the elevator button you press, right? Sent by pressing elevator button. Elevator button. But this controller will require more than one bit to represent all the unique floors it is in, right? And based on the input or the button you press on the inside the elevator, it might go to a another state, the next floor, right? Yeah. So we will see another example. Okay. Now we will see a computer example. Okay. So I will draw a finite automata and it is having three states. Okay. And we will see what is the language that is recognized by this automata, and or what is the, in easy language it means what does this automata do, okay, or compute. Okay. Okay. Q, Q2, Q3. Okay. So this is a finite automata and its name is M1. Okay. This name is M1. And what we have to, this is the state diagram for this machine M1. Now, uh, we have to identify what does this machine computes. Okay. So this state Q2 with two circles represent an accept state. Okay. This is an accept state. Okay. Accept state means that the input was a valid input. It will give an output true or accepted, and any other string which ends means, we will see an example. Okay, what is the meaning of a not accepted or rejected input? Okay, suppose we give an input of 1101 to this machine. What will happen? It will read the input one by one. Okay. It will read this in it will start reading the input. Okay, first it read a 1. It is initially, this arrow means the start state. So the machine was in Q1 state, it saw a 1, it went to Q2 state, but our input is not finished. It will read the second bit of input at state Q2. If you see a 1, it will stay in Q2. Okay, and when it saw a 0 at Q2, it will go to Q3. And when it this is a comma. Okay, when it saw the okay, we have seen a 1, a 1, a 0, right? At state Q3, when it saw the input, next input 1, it went to Q2. Now our input has been finished, reading the input has been finished, and we have ended at the final state Q2. That means this is a valid string that has been given as input to this machine. Okay. Now, if we keep on checking a number of inputs to this machine, okay, and we will see another example that will not be accepted by this machine. Okay, we will see 1 0. Okay, a small one, 1 0. Okay, first we read the input 1, we were at Q1, we go to state Q2. At Q2, we saw the next input was 0, so we end up at state Q3. Okay, now there is no more further input at Q3. That means we did not reach Q3 is not a final state, it is not in the two circles. That means our machine would say this is an invalid input, invalid input. Okay. Now, like this, if we keep on checking a number of strings and see whether they are accepted or rejected by this machine M1, we will find out what this machine accepts is any number that ends with the string 1 any string that ends with a 1, cause at input 1, any number of zeros we are staying at q1, and whenever we are seeing a 1, we are ending up at q2. That means this will accept any strings that end at 1 or after any ones if it is ending with even number of zeros, right? Then after the last one, if it is ending with even number of zeros, then it will be a valid input for this machine M1. You can try out giving a number of strings to this uh, machine, and you will find it accepts any strings that end in a 1 or after the last one. Because see, again after this one, if you have a 0 1, then it is accepted, but because it is ending with a 1. But after the last one, if you end with the 0 0 2 or 4 or 6 zeros, then also it is a valid input. Okay, so yeah, so this is all for this video. In the next video, we will be seeing the formal definition of a finite automata, or the mathematically how we represent a finite automata. So bye bye, take care, and keep exploring and practicing theory of computations.